Can you imagine a day where all particle accelerators disappear? Hi, my name is Inkiro Badike, and I'm a former intern at the International Atomic Energy Agency, Nuclear Science and Application Department Physics Section, and an all-round particle accelerator enthusiast. And I'm so happy to be here to tell you all about particle accelerator applications. Now, this will be through the lens of a story where all products that use accelerators disappear or the effect of processes involving accelerators are reversed. Now, this will be quite a bizarre story, but hopefully entertaining and something that you will remember for some time to come. So let's get into it. And now we get on to the question of what is a particle accelerator? Well, on screen here, I have a few. Here's one, here's one, here's another one. Some are in the shape of circles, others are in the shape of lines. Some fit in rooms, others straddle borders. Let me just interject to tell you about the most famous particle accelerator in the world, the Large Hadron Collider, part of the CERN science organization. The circumference of the Large Hadron Collider, or LHC for short, is 26 kilometers, and it is primarily used for high-energy physics research. But even though they have different shapes and sizes, all those machines have four things in common. The first one being a particle source that produces the charged particle. It can be a proton, electron, or ion. The second is a composite device to add energy to the particles and speed them up by applying a static or oscillating electric field. The third is a vacuum system to remove and keep unwanted particles out of the accelerating tube. And these are usually ultra-high vacuums, especially in the ones used for research and development. The last thing is a system of electromagnets to steer and focus the particle beam as it makes its way around the machine. So, what do particle accelerators do? Well, they produce particle beams and light. Particle accelerators represent a versatile and reliable way to produce radiation, either in the form of particle beams. On the right is an arduous rendering of a particle beam. Like we said in the previous slide, it can be made up of protons, electrons, or ions. And on the other side of the screen, we have a tungsten target, which plays a crucial role in how you turn an accelerated particle beam into light. And unlike radioactive sources, the radiation can be turned off in a particle accelerator once itself is turned off, thus making it a safer option. So now, let's get into a story where you are the main character. All particle accelerators have disappeared, but you don't know it yet. It's a cold winter morning where you live, and the first thing you do when you wake up is head to the bathroom. You go on to turn your tap, but nothing comes out. Unfortunately, where you once had PEX tubing, you now have copper piping, and they have burst. Plastics are made out of polymers, and PEX, which stands for cross-linked polyethylene, is an example of a cross-linked polymer. And these cross-linked polymers are stronger, more heat-resistant, and something that's missing for you, unfortunately, on this catastrophic day, more burst-resistant. And cross-linking is a mechanism that can be achieved with a particle accelerator, in this case, an electron accelerator. So this is how the process goes. So polyethylene, which is a long chain of carbon and hydrogens, are subjected to high energy electron radiation. So I have depicted it here with these squiggly lines. This ejects a hydrogen bond. And now, since something is missing, in order to make itself more stable, the carbons in the molecule rejoin to form a much stronger bond. And now we can join smaller polyethylene molecules into much longer chains of molecules. And this is responsible for these improved characteristics. So now the bonds have broken and by the electron radiation, and they have reformed in a much more beneficial way. And in this case, the material is now called PEX. And burst resistance is just one of the many characteristics improved upon cross-linking. You can make plastics more resistant to fire and to abrasion and corrosion with this process. And while cross-linking can be done chemically, doing it with a particle accelerator is the most environmentally friendly way because it avoids the use of harmful chemicals. So your pipes have burst, and naturally you want to call your plumber. So you reach for your phone, and no matter what you do, it doesn't turn on. It just doesn't work. Unbeknownst to you, the process of ion implantation has been reversed, a process that involves particle accelerators. Now, ion implantation is a part of the semiconductor manufacturing process. The chips which can be found in your phone and in many other electronics for that fact can be considered as the brain. And these chips are made out of semiconductors. And now there are many steps involved in creating these chips, but one of the most crucial steps involves the use of a particle accelerator. This process is known as ion implantation, and it is essentially the addition of boron or phosphorus or some other atom into the silicon, which is the main material of your chip. And this improves quite a few characteristics of the chip, the most important of which is the conductivity. And this process is done with an ion implanter, which can be seen here on the left. An ion implanter is a type of ion beam accelerator, and although it's different to the electron accelerator we were talking about in the previous slide, you can see that it still has some of those key fundamental parts that make it an accelerator, like an ion source, magnets, and an acceleration tube. So particle accelerators are important to the semiconductor manufacturing process, and semiconductors are really important to our economy as a whole. On the screen here, I have a graph of auto production in the US, and I just want to bring your attention to this region here around the time of the pandemic. This drastic decrease in car production was in part due to the infamous semiconductor shortage that happened around that time. And while it had nothing to do with particle accelerators, can you imagine if particle accelerators did actually disappear, thus affecting our ability to make semiconductor chips? Let's take a break in the story to hear more from you. Earlier I mentioned the LHC as an example of possibly the most famous particle accelerator in the world, and it is used for high energy physics research. But can you take a guess at what percentage of particle accelerators are used for industrial and commercial purposes, as we have talked about so far? All right, so your pipes have burst and you can't get a hold of the plumber because your phone doesn't work either. But whatever you do, you're not missing the doctor's appointment that you have scheduled for later in the afternoon because it took you months to get it. Unfortunately, you don't know it yet, but your day's about to get worse. You get to the hospital and they're not letting in anyone who isn't on the verge of dying. Why? Well, they want to prevent infection because all their PPE equipment, as well as other medical accessories and equipment, are in short supply. The facilities that sterilize them are not able to do so anymore because their electron particle accelerator has disappeared. Particle accelerators provide an efficient way to mass sterilize medical equipment, a process that has been in use since the 1960s and is done with the use of an electron beam accelerator. This short clip provides a little more explanation.
The e-beam sterilization. The e-beam sterilization process involves exposing products to a high-energy electron beam that interacts with the product, disrupting the DNA chains of any microbes. This method offers the advantage of sterilizing the product in its final packaging.
In addition to medical sterilization, tens of millions of patients receive accelerator-based diagnoses and treatments. IEA's initiative, Rays of Hope, hopes to expand access to advanced cancer therapies based on nuclear technologies, just like linear particle accelerators. So, to recap, your pipes have burst and you can't call the plumber. You missed a doctor's appointment that you have been waiting months to get. Well, at least you can look forward to an evening out at a museum with friends. You have a keen eye for history and you can't wait to see the new Renaissance collection. Unfortunately, you start to notice something wrong. The information cards don't have much information, artifacts look like they're decaying rapidly, and there are some questionable looking pieces in this new collection. Well, what does this have to do with particle accelerators, I hear you ask? Well, particle accelerators help analyze, authenticate, and preserve historical objects. Ion beam analytical techniques like PIXI and RBS are top candidates for the non-invasive analysis of cultural heritage objects. And unlucky for you, all the information gained from these analyses are all gone. In any case, this is how it works. Ion beams are used to probe the sample. This stimulates a nuclear reaction, that is the release of radiation like X-rays or gamma rays, and the energy of that radiation as well as the amount are measured by radiation detectors. The result is a spectrum which is then processed with relevant software or code. And this spectrum helps to find out the type and concentration of different elements found in the sample. So suppose a piece has come in, supposedly a Renaissance painting. You can use accelerator-based analytical techniques to determine the type of pigment. For example, deep blue pigments from the Renaissance time should contain lapis lazuli, a precious stone used since ancient times. Non-invasive accelerator-based analytical techniques can help to determine if it is indeed the case. I remember during my time working at the IEA on improving the web presence for the Accelerators for Heritage initiative, I learned of researchers who are working on determining where in the world a sample of lapis lazuli pigment is from, whether that be Afghanistan, Russia, or Chile, which could further help in the authentication process. Lastly, accelerator-based analytical techniques can help us find out the mechanism by which cultural heritage objects decay and give us a clue in how to preserve them for generations to come. So, your trip to the museum was a little disappointing, but hey, at least you have a planned holiday to look forward to. Your flight's quite late at night, so things should be quite quiet at the airport, right? Well, wrong. The X-ray scanning machines, which are all based on particle accelerators, have disappeared, and security lines are longer than ever as the authorities scramble to find a solution. From luggage screeners to whole-body scanners, the X-ray irradiation used to detect if passengers are carrying something that they aren't supposed to be carrying are all produced using particle accelerators. One of the most interesting uses of a particle accelerator I have seen is at cargo ports, where they use them to screen cargo ships from distances as much as a couple hundred meters. A particle beam is directed at a shipment, and this induces a nuclear reaction, kind of like how we talked about with cultural heritage analysis. And this reaction or signal will be characteristic of the material which it comes from. This technique is known as active interrogation. When it comes to nuclear forensics, accelerator mass spectrometry is the name of the game. Accelerator mass spectrometry, or AMS, is a technique where you insert some samples from a material you're trying to study, you accelerate it, and use a magnetic field to deflect its path. The degree of deflection tells you about the mass of the elements in the sample you are trying to detect, as well as the ratios between isotopes. Accelerator mass spectrometry is the only technique capable of analyzing uranium-236 to uranium-238 ratios in the 10 to minus 13 to the 10 to minus 10 range. That's an incredibly small ratio. Well, if you've never imagined what a day without particle accelerators looks like, well, now you know. And in fact, there are so many other particle accelerator applications in diverse domains of society, such as radioisotope production, food preservation, scientific research, water treatment, reducing acid rain, and even coloring gemstones. And if you're interested about finding more about those particle accelerator applications, I have some resources here for you, some of which are sources for this presentation, including an interesting article from Fermilab. This article about accelerator use for security and defense, from which I got the information about using particle accelerators for nuclear security, as well as the IEA Accelerator Bulletin. I want you to remember about particle accelerators. They come in all different shapes and sizes and produce diverse types of radiation. The applications of particle accelerator technology can be found in diverse domains of society, from the improvement of materials to cultural heritage analysis and nuclear security and beyond. And if you have any questions about such, feel free to connect with me on LinkedIn and send a message, or to email me to the email address shown on screen. And thank you to Bite Size Nuclear for giving me the opportunity to share all about my passion of particle accelerator and their applications. Thank you.